Hello, everybody, and welcome to another episode of Tim's Math Class. In this one, we'll be doing something different today. This is not going to be directly a material science lecture for sure. This is going to be applications of the math that we're doing with Fourier transforms, and in particular, we'll be looking more on the signals side of things, which is not directly material science, but is important to just engineering in general. If you're working on systems, there's probably signals involved, and understanding frequency behavior is very helpful to that. In the next few lectures, we will come back to material connections and do some of that to finish out the semester, but this really is focused more on just getting a better understanding of the math, getting some more physical intuition for if you have a signal that's a function of time, what does that look like as a function of frequency? How do these sorts of things move back and forth between each other to give you complementary views of a particular function? Now, what we're looking at here is not slides. Hooray. Everyone is happy, no slides. This is just my audio workstation, and you can maybe even see in the background of the recording, oh, here you are, signal. So this is the f of t that you're seeing. This is the function of time that my voice is making, and you can see the envelope of this. It has this sort of periodic nature to it because of the rhythm of speech. The amplitude goes up and down, so we have this intensity versus time. As I'm talking, I get louder and quieter. But in the bottom left, what you're seeing is the FFT, the fast Fourier transform of my voice as I'm talking. And we'll start with this, and then I'll add in a bunch of other examples. I have these other windows and other tracks open for a reason. Spoilers, there's going to be music involved. And what we're seeing is as my audio signal gets louder and quieter in time, the computer is calculating the Fourier transform of that, so we're getting intensity at different frequencies. So our horizontal axis here at the bottom is frequency. Audible sound basically goes from 20 hertz to 20,000 hertz. So that's the range that we're working in. And for voices, you can see that they start in the sort of 50 to 100 hertz range for the fundamental frequencies of, I'll say, traditionally male voices, and can go up into the thousands for people who are singing at higher pitches. So if I just like hold a note here, look at those peaks, look at those peaks, look at those peaks, and they change as I make different sounds. But there was this this fundamental peak around 100 hertz, and then there was another peak at 200 hertz, and another peak at 300, 400, 500. So there's this periodic structure to the sounds that we make when we're making musical, or in that case, musical-ish notes. And it's that, I don't really want to say symmetry, but it's that periodicity of frequency that helps to make things sound musical to us. If I just take, I have some other stuff hooked up here. I wish I could see all the windows. So that's a snare drum. I'm going to turn up the gain on that track a little bit. So that's track 4. Oh, geez, make you louder. So look at that sound spectrum. It's totally different than when I was singing a note. So look at the left again. Note. Those very periodic spikes where it's a lot of this frequency, a lot of this frequency, a lot of this frequency. But the snare drum, in contrast, there's like a couple of spiky-ish things, but it's actually quite flat. There's a lot of content all across the frequency range. There's a bunch of different frequencies that are all mixed together at roughly equal intensities, whereas again, so I'm making a little bit more of a, I guess, pure sound there. It has fewer frequency components. Look at how few spikes there are. There's only like 3 or 4 main frequencies in that. And so in the one case, we had a very regular wave versus a... And this is something that we already saw in the previous examples, where the Fourier transform of a cosine or a sine wave was just a delta function. It was one single spike, and then the inverse is true as well. So when I hit the snare drum, it just makes this very fast spike. Just, right? There's not a long waveform there. It's just a pop. And that means that there's lots and lots of different frequency content in order to build a wave pulse, a wave packet that is a very short bandwidth in time. This complementary nature of things that are very limited in one domain are very spread out in the other domain. That's our uncertainty principle. Now, if I actually want to make a sine wave, I might have to do some more dynamics here. That's not a sine wave. One sec. There's a sine wave. And I bet if I zoom in here, I know I have 1,000 windows open. I need to be able to see all this stuff. I don't think I'll be able to see it in real time. That's too bad. But what we'd see here, if I could zoom in a little bit more, it won't work, that's unfortunate, is we would just have a sine wave in the waveform. And in the Fourier transform of that, so here's our Fourier transform of the sine wave on the left. It's a single sine wave in time, which means it contains a single frequency. And that's what we see here, a big spike at 250 hertz or so, which is a C. And then if I play one octave up, there's a spike at 500 hertz. One octave is doubling the frequency of the sound. And if I go up another octave, that should double it again. I'll be at about 1,000. And there it is. Now, if I start to mix these things together, there's a fifth, that's the musical interval of a fifth, and it's 1.5 times the frequency. I've got about 250 and about 400 being mixed together here. So I'm not going to go full music theory on this, but the point is, as I'm mixing different sine waves together, we start to get a more textured sound. It has more frequency components to it. And if I extend that and mix a whole bunch of sine waves together, then, all right, so this should now be, listen to that. The quality of the sound is quite different. Going back to the sine. It's the same pitch. It's the same fundamental frequency. They're both sitting at 250 hertz, 251 hertz. And that fundamental frequency, the 250, that's the same for all of them. But the triangle wave, so that's what I'm playing now, and we did this in the homework. You did the Fourier series for a triangle wave, and you find this decreasing amplitude of regular frequency components. That's what we see in the plot of the Fourier transform. There's lots at 250, and then there's a spike at 3 times that, and then 5 times that, there's a little bit less, and then 7 times there's a little bit less, 9 times a little bit less, 11 times a little bit less, and you have this converging series where all of these things summed up make a triangle. Okay, so that's a thing. And then there's what's called a saw wave. So that is a different kind of waveform. And you can see there's lots and lots of frequency content there. And it sounds noisier. It doesn't sound like the snare drum. It's not that noisy. But this is part of what we perceive in terms of frequency, is that sounds that are more like noise have lots and lots and lots of different frequencies mixed together. And this is the same thing just in a generic signal sense. A noisy signal is one that has frequency content besides the fundamental information of the signal. That's what noise is it's other intensities at other frequencies present that are not what is desired. If I play just some different sounds here. So again, sounds a lot look at how many different frequencies are present in the signal, but it still sounds like a note because there's still this periodicity. The fundamental frequency and that one and that one and that one, and they're regularly spread out in frequency space until we get to the higher end, and then that's where all that grit is coming from. Now, for other things that are involved here, if I have my guitar, and this is at sort of a medium distortion level, I'm going to play a couple notes and I'm going to change the amount of distortion. Look at what happens in frequency space. So we're not looking at what the waveform looks like in time, we're saying what frequencies are present in this signal. So first we'll have a clean sound. Not a lot of frequency components. And they're very regularly spread out. Okay, great. Now we'll go up a step in terms of crunch. See how that's different from before. Lots of extra high end present in that signal, and it's not as periodic as it used to be. The fundamental notes are still there, or rather the fundamental frequencies that define the note are still there, but we're mixing a lot of other stuff. And now the distortion gets a little hotter. We'll do one more. All right, couldn't help myself. Now, what's the point of all this? I mean, there's a lot of points of this, but the first point I want to make is that you can gain a lot of information about a signal from what its frequency content is. And I know we're doing all this dynamically because I'm talking in real time and I don't want to have like 800 windows open to look at all of the things. But if I could just hold a note and just freeze that Fourier transform and get a single function and be like, okay, I grabbed my signal, I saved it, I preserved it, this is the frequency content, then you could reverse transform that. You could actually calculate what did the sound like in time based on the frequencies that it contains. And so a lot of signals processing, which includes audio engineering, is about that. It's about looking at the frequency content and then modulating the amounts of different frequencies, increasing the amplitudes or decreasing the amplitudes of the function at different locations in frequency space to change how it comes through in time. Okay, a few other examples coming up. Now, going back to the vocals here, again, if I just sing like a regular normal note, Om. Okay, so you see that periodic structure. What I'm going to do now is I'm going to do a frequency sweep and watch what happens. If I take a single note, that's what vowels are. Different vowels are different sets of overtones. You are changing the shape of your mouth. So this is starting to get to the actual physical engineering side. When we think about acoustics and vibrations, you change the shape of the resonator, and that's how you control the frequency content. This is going to be relevant in the next two lectures when we do get back to the material stuff. The frequency structure of your resonator, what does that mean? Well, I've been talking about space here. I'm not been talking about space. I've been talking about time, omega and t. But remember, we also can talk about waves spatially. You can talk about where the wave is distributed in space, at what positions x is a wave intense or not intense, and you can convert that to k. You can talk about the spatial frequencies of a wave. Well, if my resonator has a certain spatial structure, so I'm talking about making sounds, making vowels with my mouth, my teeth are in certain positions, my tongue is in a certain position, my lips, like all of the muscles in my skull, all that stuff is moving around as I make different sounds. And if you take that resonating spatial structure where everything is, you can calculate the spatial frequencies of that through a Fourier transform. And that's going to help you understand what the different resonant frequencies are, what different vibrational modes will be able to live most stably in that structure, in that physical structure. So I'll just say the word now, diffraction. That's where we're going with all of this. That's kind of the punchline. So there's the punchline. See if you can figure out the joke. But yeah, with all the different sounds that we make in speech and in singing, whatever, the things that we do with our voices, even if they're on the same pitch, that fundamental frequency doesn't change. So again, I have no shame. But like all of those pitches were just sitting in that fundamental note at 150 hertz or so, just stayed there. All of the other frequencies being mixed in with that one that determine not the note you hear, but what that note sounds like. What vowel is it on? What is the timbre? What is the sort of color of the sound? That's all of the other stuff coming in. So there you go. I don't want this video to go on forever, partly because the Michigan-Ohio State game is about to start, and that's important too. But I hope you found that interesting, got something fun from it, and really do think about, okay, what are those connections to materials and structural engineering and that sort of stuff? Because it is there. I like to explain this a lot in terms of signals processing, because things that you can hear, just for some people, not for everyone, but for some people, it really is easier to understand when you have that particular sensory path. And it's not just all like, okay, I'm calculating things with f of omega, FOT, whatever. The math can be helpful, but it's not the only way to gain an understanding of this stuff. At the end of the day, we are going to come to materials applications, but I wanted to, as I said, spend this time looking at some Fourier transforms to look at the content of signals in frequency space, and for you to have a way to perceive those signals as a function of time with your ears, and then to look at with your eyes what the frequencies are, and to see some of those interrelationships between the two domains, between, in this case, time domain and frequency omega domain. As we move forward, we will be looking at spatial structures, as I've hinted toward the end here, and spatial frequencies, and finally use that to talk a little bit more about material science before the semester wraps up. So there you go. It was planned, but that was not scripted by any means. So I hope you found the rambling productive, but you know what to do. Send me your questions and we'll take it from there. So there you go. In the next lecture, we will look at the fast Fourier transform, which is what is the mathematical algorithm? What is the computational implementation of that algorithm that is used to take these waveforms and to, the name's right there, to do it fast, to do it quickly, convert them to frequency space, essentially in real time, in order to be able to perform calculations that are both accurate and useful on these signals. So tune in next time to learn about FFTs, and I will, of course, see you there.